Hi everyone, welcome to this webinar on machine learning and meaningful games. So today we are very happy to have Desik Rengarajan from Hewlett-Packard Labs. So Desik did his PhD at Texas A&M University under the guidance of Srinivas Shakotai and Dilip Kalatil. And well, thanks a lot, Desik, for accepting to present your work. The floor is yours.
Yeah, thank you very much for the kind introduction and for the opportunity to present our work. Hi, I'm Desik Rengarajan. I'm a research scientist at Hewlett-Packard Labs, and I'll be presenting our work on reinforcement learning for mean field games with strategic complementarities. So this work was done when I was a PhD student at Texas A&M University, and it's jointly done with Dr. Kiob Lee, Dr. Dilip Kalatal, and Dr. Srinivas Shakotai. So before I start, I would like to provide some motivation to what strategic complementarity is and why we follow this structure of this problem and why we look at this structure. So strategic complementarities refers to a set of properties wherein the marginal returns to increasing one's strategy rises with the increase in the competitor's strategy. So what does this mean? So a strategic complementarity exists if informally higher or stronger actions by other players increase the return to higher or stronger actions for a given player. So in some sense, there is some sort of alignment between one player as well as the population. Right. So there are a lot of examples that follow strategic complementarities. So for example, in online social media, if many people are spending a lot of time on Facebook, then you as an individual spending more time on Facebook will give you more gratification. Similarly, in online marketplaces, for example, if Uber attracts many customers, it means that many drivers are doing a good job. So each driver has an incentive to do well. And another example that we gave, and because this paper was written right at the beginning of the pandemic, was essentially the idea of COVID-19 or virus spread. That is, like if many people are following social distancing or are taking measures such as wearing masks and washing hands, then you doing so will be more effective. So all of these kind of systems follow the idea of strategic complementarities, wherein stronger actions of the others means more benefit for you doing the same, which essentially implies you take stronger actions, and vice versa. So why do we look at this, or what was the motivation behind us actually following this structure? One is that it aligns with some of the real world problems at that time, and the second is also that analysis of mean field games is generally tricky without a lot of structure. And this is one way of imposing some structure to the problem. Right? So what is the problem formulation that we are looking at? So in our work, we consider stochastic games, where a stochastic game is essentially a MDP with one or more players. Or stochastic games can also be viewed as games with transition probabilities played with multiple players. So a stochastic game formally is a tuple where you have a state space S, an action space A, and n players, and a discount factor of gamma. And you have a reward Ri, where it's a reward for player I, and it is a function of the states of all the players and the actions of all the players, and it maps to a real number. And lastly, you have the transition kernel P, which essentially denotes the state transitions of, and it's also a function of the states of all the players in the system and all the actions taken by all the players in the system. Right. So what is the problem? And firstly, a solution to a stochastic game is essentially a Markov perfect equilibrium. But however, this equilibrium is hard to analyze or achieve. And this is mainly because, as I alluded to before, the curse of dimensionality kicks in as the number of players increase, because your transition kernel depends on the states and actions of all the other players, so does your reward function. And second, modeling real world problems as a stochastic game is kind of not plausible, because in many real world applications, as the number of players becomes large, it becomes increasingly difficult to believe that every individual player tracks the exact behavior of every other player, because that's not how people work. Like, for example, if you're trying to model, let's say, disease spreading, you don't really track the behavior of every other player, but rather track the behavior of the population. Right? So that's more in line with how you can formulate real world problems. And so this naturally alludes to the formulation of the mean field regime, right? So the mean field regime is essentially an asymptotic simplification or approximation of stochastic games with a large number of players. So we first define mean field in this work, and in this work we use state-coupled mean field. So our mean field is only defined over states. So we define a mean field Z of players where Z of S is essentially the empirical distribution of players over the states in the system. So here I is an indicator function, and Si is the state of player I. And what mean field does is that it ignores the identity of the players and just accounts for the distribution of players. So you don't really track the individual behavior, but rather actually track the population or how the population performs. So formally, a mean field game is an approximation of stochastic games where you have a reward function Ri. So now this reward function Ri is a function of the state of the individual, Si, the action of the individual Ai, and a mean field Z. It's not a function of individual states of the other players, but rather just the mean field. Similarly, the transition kernel denoted by P is again a function of the state of the individual player, action of the individual player, and the mean field. So the next state is again drawn from this distribution. So, and again, as I mentioned before, this is an approximation and becomes more accurate as more number of players participate in the system, as well as in this particular work, we consider state-coupled mean field, wherein the mean field is only dependent on state, but you can also have action-coupled mean field as well. And we also consider homogeneous players, where the reward function of all the players is the same. And for analysis and for this framework, we consider finite state and finite action. So these are some of the assumptions that we make in this particular paper. Okay, all right. So now that I've explained what stochastic games are, what mean field games are, we would like to talk about what the solution of a mean field game or mean field game is. Like Markov perfect equilibrium was for stochastic games, the mean field equilibrium is for mean field games. So for any Z, the player's objective is to find the optimal policy mu star. Right? So what this optimal policy mu star does is that it maximizes the infinite horizon discounted reward of that player. And so you can think of it as follows. So if you fix a Z, what happens is that the problem boils down to a Markov decision process, right? Because your reward function is conditioned on Z and your transition kernel is conditioned on Z. So for a given Z, it essentially becomes a Markov decision process, and then you can solve, let's say, value iteration, and it'll converge to a unique V star or a unique value function for each Z. Right? So that's the objective of each player. That is, each player observes what the mean field is, and then he solves or they solve essentially the value iteration to find out what their unique V star is, right? And essentially the policy as well. So now, given a pair of Z, that is given a pair of the current mean field and a strategy or policy. So I'll be using strategy and policy interchangeably because one is for reinforcement learning and one is used in the game theory, but pardon me if that's confusing. So given a pair of mean field and strategy, the mean field evolves according to something known as a discrete time Makin-Blasso equation. So here Z dash is the next mean field, is a function of phi, Z, which is essentially a function of phi, Z and mu, right? So where the next mean field is given as follows. So we can break down the function phi in the following sense. So this is pretty easy to parse. So suppose you have a mean field Z that is given to you. Your transition kernel can be conditioned on that mean Z. So this becomes essentially like a transition kernel in a Markov decision process. And you multiply that transition kernel with a policy or a strategy that essentially becomes a Markov chain. And you multiply that Markov chain with the current mean field. So what you're essentially trying to do is you're trying to see what a one-step evolution of the Markov chain induced by that policy and mean field is. So that's the discrete time Makin-Blasso equation. So again, the mean field equilibrium is defined as a pair mu star and Z star for a policy and mean field such that both optimality and consistency conditions are satisfied. So a mean field equilibrium is achieved when you have these two important conditions. One is optimality and the other is consistency. So what is the optimality condition? So suppose you have this pair mu star and z star. You fix your z star, and then you find the set of optimal policies, right? By solving value iteration or any method that you'd like. And your mu star here should belong to that set of optimal policies of z star. Secondly, what is a consistency condition? The consistency condition is, suppose you have a z star, and then you fix your transition kernel for that particular z star, and then you compute the Markov chain, which is induced by that z star and mu star. And your z star should be essentially the stationary distribution of that Markov chain. So that is, you feed in z star, and then you take actions according, and you reach back z star again. You take actions according to mu star, and your mean field does not evolve. So you are at a stationary distribution. Okay. So yeah, so essentially the optimality condition as well as the consistency condition. So these are the two important conditions that need to be satisfied for a Markov equilibrium, for a mean field equilibrium to exist. So now that we have spoken about these few concepts, in this paper, we introduce some randomness to the equilibrium. And this is atypical in previous works or in the stochastic game regime, but we actually introduce it mainly for the learning aspect. So what we need is that for learning, we need to add some sort of exploration component to our algorithm. And the one way of doing this, or the way we do it, is by this concept known as Seltin's trembling hand perfection. So trembling hand perfect equilibrium is essentially is an idea which we borrow from, which was used for normal games, and it's essentially a refinement of the Nash equilibrium. And so what does Seltin's trembling hand perfect equilibrium does is that it accounts for the possibility of off equilibrium play, where players may choose unintended actions with small probability. But I think the motivation was that in game, when you're playing games, you might have a trembling hand where you might slip and play an unintended action. Right? And this also aligns well with a lot of real world cases where not every player might play the optimal action at all points in time. They might play an off equilibrium action some points in time. Right? So what this does is that it adds an epsilon randomness to the off equilibrium play. And in essence, what Seltin's trembling and perfection does in our case is that it constrains the policies or strategies that we are trying to learn to be mixed strategies or to be epsilon random policies. So there's an important thing that I'd like to point out is essentially the difference between trembling hand policy as well as epsilon greedy policy. Right? So epsilon greedy policy is something which is used in reinforcement learning, and there's a slight difference here. So under epsilon greedy policy, the agent computes an optimal policy and then adds the epsilon randomness to it, right? But in trembling hand policies, what we do is that we compute an optimal trembling hand policy while accounting for the impact of it on the value function. So our value function takes into the fact that like our policies are trembling hand policies, and this will become clear in the next slide. So we now define a variant of the Markov, we define a variant of the mean field equilibrium called trembling hand perfect mean field equilibrium. And this essentially generalizes Seltin's trembling hand perfect equilibrium to the dynamic game setting. So what we do is that let pi epsilon essentially is the set of epsilon randomized policies. So what this does is that it places most of the mass on one of the actions, let's say AS, and then it places epsilon by cardinality of a minus 1 on all of the other actions. So essentially what you're trying to do is your set of policies are such that you place 1 minus epsilon mass on your best action, and you basically divide the epsilon amongst the rest of the actions. So I think this will become clear why we do this as we move forward in the talk, but this is the set of policies that we constrain ourselves to be in. Right? So now we define what a trem. Is there a question? Or?
Oh, sorry, I had one quick question. So here
Yeah.
you define pi epsilon as a set of all policies that are epsilon randomized, whether they are epsilon greedy or not, it doesn't matter, right? You take all epsilon, in particular, it contains the epsilon greedy policies for some value function, but it also contains any epsilon randomized policy. Okay,
Yeah.
thank you.
So yeah. So now we define what the trembling hand perfect MFE is. So similarly, so trembling hand perfect MFE is again a pair of mu star and z star of a policy and a mean field, such that both the optimality and consistency conditions are satisfied. And here, your mu star is argmax over mu belongs to pi epsilon, which is essentially the set of epsilon randomized policies, and the consistency condition is the same, right? So mu star belonging to the argmax of this constraint set is called an optimal trembling hand strategy. And so this mu star is strategically consistent because the value function accounts for the randomness, because we have computed this value function by accounting for the randomness. And for example, in let's say in the in the mean field equilibrium case, when we wanted to compute mu star belonging to argmax of mu v of mu z star, here we add the epsilon randomness after the policy is computed, so it's not strategically consistent. So this is again the difference that I pointed out between using Sultan's trembling and perfection versus the epsilon greedy strategy. Okay, all right. So now we would like to formalize what we mean by strategic complementarities. So essentially, let gamma be a stationary mean field game, then gamma is considered to be a mean field game with strategic complementarities if it has the following property. You have your reward function, which is non-decreasing in S, supermodular in SA, and has increasing differences in SA and Z. So what this essentially does is that it's a way of formalizing the notion that there is alignment between the state actions of a single player and the population state of other players. Right? So this kind of formalizes the notion of strategic complementarities. And also the transition probabilities is stochastically supermodular in SA and has increasing differences in SA and Z, and is stochastically non-decreasing in each of SA and Z. And so what does this do? This ensures that larger states and or larger actions are now more likely to lead to larger states in the future. So what does strategic complementarities essentially do? It kind of induces a herding property where you have higher actions have higher impacts in higher states when others are in higher states. So you have this herding mentality towards going to higher states or going towards good states. Right? So what do we show in our work? So in our work, we essentially show the existence, we first show the existence of the trembling hand perfect mean field equilibrium. And that's our first theorem. So let gamma be a stationary mean field game with strategic complementarities. Then there exists a trembling hand perfect mean field equilibrium for that game gamma. Right? So this proof requires like several steps, and which I'll go over right now. But intuitively, what we want is we want to satisfy the optimality. We want to show that we satisfy the optimality condition as well as the consistency condition. And in order to show that we satisfy the consistency condition, we need to use some sort of a fixed point theorem, because the consistency condition essentially says that you have a fixed point. So in this work, we make use of Tarski's fixed points theorem. And this has been shown in previous work as well. I think there's a work by Adlaka and Johari, which show it for which shows strategic complementarities for mean field games, and then we extend it to the trembling hand perfect equilibrium, and we also show the learning component. Right? So what are the? So now I'd like to just go over like, sorry, yeah.
Oh, sorry, one quick question. So in this theorem, do you fix epsilon a priori, and you mean that for every epsilon? Okay, so for
No,
every
epsilon is
epsilon there
fixed.
exists.
Yeah.
Okay.
Yeah. So we
I see.
fix an epsilon.
Okay. Thanks.
Yeah. Even I think that's a good point. Like even when we define our set of epsilon random policies, our epsilon is fixed. So we fix an epsilon for our problem. Yeah.
Okay. Thanks.
So our proof has several steps. So what's the first step? So the first step, what we show is that we show that V star of Z, which is the optimal policy for the mean field Z, is non-decreasing in S and has increasing differences in S and Z. Moreover, mu star of Z, which is the trembling hand policy, which is computed, is stochastically non-decreasing in S and Z. So what does this mean? This means that the policy that we get essentially pushes our agents to higher states. So that's kind of what we say, and when other people are also in higher states. So that's what this step one does. And step two, what we show is that the McKean-Blasso update, which is essentially the one-step transition, is stochastically non-decreasing in Z and mu, provided that mu is stochastically non-decreasing in S. So what does this mean? This again means the same thing, that when you do this one-step McKean-Blasso equation, you're being pushed to higher states, given that your policy is as defined in the first step. So now step three essentially is combine step one and two. So suppose we define a map epsilon, which goes from states to states, which is essentially the McKean-Blasso equation of Z and mu star of Z. So notice that this is mu star and not just mu, where mu star is stochastically non-decreasing in S as provided by step one. Then from step one and two, you can say that this epsilon is stochastically non-decreasing function in Z. So what we have essentially shown that using mu star here will essentially push you to higher and higher states, right? That is, will push the population towards higher and higher states. And then by Tarski's theorem, you can show it's a fixed point. So this essentially ensures that we have consistency. And since mu star is the optimal policy, we have optimality. So both are satisfied. So that's kind of the proof outline. And I think you could go over the paper for details if needed. Okay, so where are we right now? So what I've done till now is that we have explained what stochastic games are, and then I went over what mean field games are and what strategic complementarities is, and then the mean field equilibrium and trembling and perfect mean field equilibrium, right? And we also established the existence of trembling and perfect mean field equilibrium for mean field games with strategic complementarities. So now what we're going to do is we're going to show how we can compute the trembling and perfect mean field equilibrium. And we're going to first assume that the model is known. But there's something to note here is that there is no general algorithm for actually finding mean field equilibrium or trembling and perfect mean field equilibrium in mean field games. And mean field games with strategic complementarities is an exception. As I mentioned before, there's a work by Adlaka and Johari, which essentially solves this which essentially shows the existence of mean field equilibrium in dynamic games with strategic complementarities. All right. So now I'd like to again go over a few more things, which is slightly different because we are restricting ourselves to the epsilon randomized policies. We don't do Q learning anymore, but rather we don't do normal value iteration, but we do a variant known as the generalized value iteration. So for any Q function, we define our policy to be as follows, which essentially is that you place 1 minus epsilon mass on the highest actions, and then you divide the epsilon mass amongst the other actions. And we define our generalized Q update as follows, which is essentially the expectation over actions of the policy times the Q function. And you can also define a TQ value operator FZ as follows, which is essentially very similar to your normal Q learning TQ operator, but here we, instead of taking max over all actions, we do we just take it according to the policy. And it can be shown that like this is a contraction mapping and there exists a unique fixed point, and we call this TQ value iteration. And this is again presented in works in older works in reinforcement learning by Sapaswari and Littman. Okay. All right. So now I'd like to go over our first algorithm, which is essentially the computation of the trembling hand perfect mean field equilibrium. So by computation, I mean that you know your transition kernel, you know your reward function, and you just want to compute what the mean field equilibrium is. So our algorithm goes as follows. You start with an initial mean field Z0, and you iterate over mean field Z0, Z1, Z2. So for the mean field ZK, you compute the optimal Q function using the generalized value iteration. And once you have the optimal Q function, you can find out the trembling hand policy according to that Q function. And after that, you can compute the next mean field using the McKean-Blasso equation, just a one-step McKean-Blasso equation. So there is to note that here Z, we're not trying to compute the stationary distribution, but rather just the one-step McCain-Blasso equation, and that's enough for us to just converge to the mean field to the tumbling and perfect mean field equilibrium. So, and then we show in our second theorem that again this then we can compute essentially the trembling and perfect mean field equilibrium using this algorithm, and the proof just directly follows from our theorem one.
Okay, can I ask you a quick question again? Sorry.
Yeah.
In this theorem 2, does it play a role that you have strategic complementarities, or could it work for any mean field game? Would you get the convergence for any mean field game, or the structure
No,
of
no, no.
strategic
This is for
complementarity?
mean field games with strategic complementarities.
Okay,
So
so you
yeah.
do use the structure. Okay.
Oh yeah, correct. So that's the first line. Let gamma be a stationary mean field game with strategic complementarities. Yes, the structure is important. Like we cannot show whether we cannot even show if a trembling and perfect mean field equilibrium exists for games without strategic complementarity. Or rather, we have not shown in
I
this
see.
particular work. Yeah.
Okay, sounds good. Thanks.
Yeah. Okay, so there are a few things that we'd like to point out here, and recall that algorithm one generates a sequence of mean fields, and the limit point is essentially the trembling hand perfect mean field equilibrium. And then due to the monotonicity property of mean field games with strategic complementarities, we have the following remark. The sequence of mean fields zk, that is z0, z1, z2 up to zk, is a monotone increasing sequence, and therefore there exists a finite k naught such that zk minus z star is less than epsilon for all k greater than k naught, where z star is the trembling and perfect mean field equilibrium. And then we will show the existence of k naught to characterize sample complexity of learning algorithms. So all of this is just to compute the sample complexity of learning algorithms. So what we're essentially saying that after a few number of iterations, you're really close to the mean field. And we'll run our algorithm up to this number of iterations. All right. So the first thing that we're going to talk about is simulator-assisted learning of the trembling and perfect mean field equilibrium, and I'll get to what this means. So before that, just to understand where we are, so we introduced the computation algorithm for trembling and perfect mean field equilibrium, and we also showed that it converges to the trembling and perfect mean field equilibrium. But here we require the knowledge of the model twice. First, we require it in order to compute our optimal Q function. And we also require it during the McCain-Blasso transition. So in both these cases, we require the knowledge of the transition kernel. So what can we say when the model is unknown? And we are going to show essentially a simulator assisted algorithm as well as a fully online algorithm. And then we're also going to show what the convergence as well as sample complexity is in these cases. All right. So just a brief overview of reinforcement learning, and this is not really a lot. So essentially, okay, yeah. So reinforcement learning is a model-free learning approach to solving MDPs without the knowledge of the model. And in reinforcement learning, typically there is a simulator that the agent could interact with and collect samples. And in the first algorithm, we assume that we have access to the simulator, and later we will get rid of this assumption. And again, similar to TQ value iteration, we can also introduce TQ learning. And this is similar to Q learning, except for we use the generalized value iteration operator that we spoke about before. And it can also be shown that this algorithm converges, and this is also an existing result by Sapaswari. And so that's the only difference when compared to the normal Q learning. And the reason why we are doing this is because of the we are restricting ourselves to the epsilon randomized policies. So what's our algorithm? So our algorithm is as follows. So we initialize the mean field Z0. So you can think of Z0 as the mean field of the real world, or you have some real world mean field which starts at Z0. Then what happens is that for each iteration, that is for each evolution of the mean field, each agent initializes their simulator to this mean field Z0. That is, you have the world, which is currently at some mean field, and then the players basically view this mean field, and then they initialize their simulator to that particular mean field, and then they perform Q-learning on that simulator, right? So they take actions in the simulator, observe the rewards, update their Q function, and obtain the policy. So observe that when they take these actions, right, the states change, but these state changes are only in the simulator and they do not affect the real world's mean field. So the world's mean field remains the same. You initialize a simulator to this mean field, and then you run your Q-learning algorithm inside this simulator. You get your policy out, and then you execute your policy in the real world, and the mean field changes. So you see that you're using your simulator in line 5 to in lines 4 to 8, where essentially you're setting it to the world's mean field, computing the uh, optimal policy, and or rather like close to the optimal Q policy, and then you execute that in the real world. Right? And we also can show that like algorithm 2 converges to a trembling and perfect mean field equilibrium, but here we have access to a simulator. I think there's a question.
Yes, there is a question about the next mean field.
Yes, yes.
Yeah,
But
so
here
the
it's
next mean
done
field is
without,
basically the function
yeah, yeah,
phi, right? So it's like,
yeah,
yeah. But
yeah.
do you use simulator? Do you use samples or
We
do
use
you use a
simulator. We
true?
use samples,
Okay.
samples. Yeah. Yeah. So essentially, as I mentioned before, lines 4 to 8 are performed in the simulator. Is there another? Okay. Yeah. Thank you. And this get mean field, as the question was before, essentially is the phi function that we talked about, and it's just a one-step evolution and not stationary computation of the stationary mean. Correct. So we essentially show a sample complexity result for this particular approach, and essentially under assumption one, where we make some sort of Lipschitz assumptions on our transition kernel reward function as well as the Markov chain. We say that if you perform this T naught number of updates, you'll be epsilon close to the mean field equilibrium after k naught steps, or 2 epsilon dash close to the mean field equilibrium after k naught steps with probability 1 minus delta. So there are some things to note here, and I don't want to mislead people in this case. So here it seems that our T naught is just logarithmic in state and action, but that's not true because you have an L here. So this L refers to the covering time of our algorithm, and this can be a function of state and action. So essentially, the covering time tells us the number of steps needed to visit all state action pairs from any arbitrary state, and that can be S times A. And again, this result here, we combined results from Evander and Mansour, where which essentially talks about convergence of Q-learning algorithm, and we combine it with our theorem 1 and 2 to basically obtain this result. Okay, all right. So where are we? So next, what I'm going to talk about is learning directly from the real world and not using the simulator that we mentioned before. Okay, so the idea is we have an availability of a large population of players in the system. Can we actually use them to learn instead of accessing the simulator? Can we make use of the fact that we have a large number of players in the system? Can we actually use them to learn? And the answer is yes, we can. And this is our our completely online learning algorithm for the trembling and perfect mean field equilibrium. So the algorithm progresses as follows. So you start with a mean field Z0, that's the mean field of the world. And then you have a strategy mu0. Then for the evolution of the mean field, each agent, what they do is that they observe the current state, that is their own current state, and they take action according to the strategy that they have. So they take action according to their strategy and they get a reward and they observe the next state. So what happens is that as a consequence of this action, your mean field actually changes, right? Because you've taken this action in the real world, you're actually changing on how the what the real world is. So all the players take actions at the same time. So we don't assume that like the mean field keeps changing across the action of each player, but rather it changes after all of the actions are taken, right? So, but essentially the actions of the players change the mean field. And what we do is that we collect all of the data, that is the state, action, reward, next state, and add it to a memory buffer. And once this is done, what we do is that we do Q-learning using our memory buffer. Whatever data that we have, we perform Q-learning. And then what we show is that doing this algorithm also converges to the mean field equilibrium. So what's the difference between this and the previous approach? In the previous approach, what used to happen was we had to go back, initialize our simulator, and then interact with the simulator and then learn. But what we say is that if we have, let's say, a large enough number of players in the system, then we can directly learn. We don't have to go back and use the simulator. But there are some caveats to this, and which I'll go over in the next slide. So the first one is that what we essentially do is we replace sampling from the simulators to collecting data from the agents, and it might cause a mismatch. And the mismatch is as follows, right? So when we collect samples, what happens is that the mean field evolves, and an optimal policy obtained using these samples is not matched with the current state distribution of the agent. Right? There's this one-step lag in your policy, and hence agents, the sample-based strategy in UK will lag the current system by one step. Because if we look at the first approach, so the simulator-assisted approach that I spoke about, you have your mean field Z0, and then you compute the optimal policy for that Z0, and then you play it. But here you're actually playing ZK minus 1 at ZK. So there's this one-step lag, right? So what we show is that due to the structure of the game or of strategic complementarities, this one-step lag of mean field will still maintain the monotonicity property of mean fields under the assumption that TQ learning converges. And what we show is that TQ learning in our case converges because of two main properties. The first one is that all state action pairs are visited at each time step k. And how do we ensure this? So we ensure this because we have epsilon randomized policies via the trembling hand strategy. So this ensures that all actions are taken, as well as we also assume regeneration, where we have a fraction of population which are being regenerated. So we have players in all states, right? So both of these ensures that our Q-learning algorithm converges, and hence we can also converge to the mean field equilibrium. And there's another small caveat here, which we also kind of used. That is, if you notice in line 7, we do not always initialize our Q function during Q learning to all zeros. We initialize it to the previous Q, and we notice that this helps with better learning. But yeah, that's one thing. And so what are the numerical experiments that we do here? And our numerical experiments are pretty simple. So I'll provide one example, and the others you can take a look at the paper. So we look at the infection spread example, where we have our state space, which is 24 states, which depicts the health level, and our action space are actions which are preventative actions that you can take. And we define our function P of S to be a decreasing function in state. So this essentially indicates the susceptibility of players. So higher health level means you have lower susceptibility. And we define something known as an infection intensity, which is IZ, which is a product of CF and the expected susceptibility of players in the system. And you can interpret this as the probability of getting infected via interaction with the population. And then we define our transitions as follows, where you take some action and then you move up a state, but then you have some W that actually pulls you back. So this is some sort of noise that pulls you back. And then you just have like when you take an action, you just move up or nothing happens. And so these are all governed by events E1, E2, and E3, which are um, three mutually exclusively events with probabilities as defined here. And zeta is also an hyperparameter. And we also define our rewards, where our rewards kind of are in line with the strategic complementarities that we spoke about. So what we observe here is,
Sorry, can I ask you a quick question? Sorry to
yeah, yeah.
interrupt. For the reward, so what does I know you mentioned it at the beginning, but what does strategic complementarity mean in this situation? Because why intuitively, why would you follow what other people are doing? Um,
So, okay. So I think intuitively here, essentially, so if let's say the population is masking, let's say everyone around me are wearing masks or like are following social distancing, then me doing so will actually help in increasing my health. If my entire population is not wearing mask or like not washing hands, then me individually washing hands or like wearing mask is less effective when compared to when everyone is wearing masks and everyone is washing hands. So that's the strategic
I see.
complementarity here, intuitively.
But could it also go the other way around by saying that if everyone is wearing masks, then maybe I don't need to wear a mask because I'm the only one not wearing a mask? Um,
Uh, yeah, but I think we don't model that in this particular
okay.
thing. But yes, yeah.
Okay, so in this
So
case, it's
again,
something like players anticipate other people's behavior and they want to behave in
yeah,
the same way because it will be more efficient in some sense. Okay,
yeah. So I
gotcha.
think even the infection spread example is also present in Adlaq and Johari, but I may be wrong. But yeah. Anyway, so what we show here is we show the convergence of our algorithm, and here is the CDF, the cumulative distribution function of over the states for a particular scalar intensity that we chose. And we can see that you have mass towards the higher states because that's the herding behavior that we expect. And again, as you increase the intensity of your infection, you have um, the population in lower states. That's why you see this curve dominates these because you have more mass in lower states. And this is the same interpretation of this curve. And also an interesting thing that we assumed for the online regime was that if you have lower number of players, you don't actually learn a lot because in the online learning, you're learning across all agents. So more the number of agents, the better you learn because you have more samples for state action pairs. And that's what we showed here. And in conclusion, so we established the existence and computations of trembling hand perfect mean field equilibrium. We showed model-free learning algorithms for learning the trembling hand perfect mean field equilibrium. We spoke about convergence and sample complexity, and we also gave an online learning algorithm for the trembling hand perfect mean field equilibrium, and we also spoke about an example of infection spread. And thank you. And I'm open for
Thank you.
questions or discussions or yeah.
Yeah, thanks a lot for your very nice talk. I think that's very interesting. There are many ideas, maybe that haven't been studied that much in the mainstream game literature so far. So yeah,
Yeah.
thank you. Do you have
Yeah.
is there a question?
Yeah, I do. Thanks for the talk, by the way. It was
Yeah.
very interesting. I just came across this work a few weeks ago, and then this what was announced afterward, and so it's a great timing. I'm happy that I got to, hear from the
Oh,
author.
okay.
I wanted to ask a couple of things, mostly about the online, like learning in the real world setting.
Okay.
Can you
Okay.
go back to slide 32, please?
Yeah.
So this is one of two questions that are unrelated, but the first question is, you say synchronous Q learning, and then you say that all state action pairs are visited at each time step. I guess that doesn't make a lot of sense to me if you have finitely many players and you're dealing with like an online trajectory. Can you elaborate on that? Why should there be a player in every state, and why should every action be taken?
So we ensure that there are players in every state. So we are not. So the way we do it is that yes, you're right. In an online trajectory, you might not have players in every state, but we assume that there is regeneration where you have some mass of players in every state.
Is that in the code? the pseudocode?
I think no, that's not in I don't think that's in the pseudocode. So I don't think that's here in the pseudocode where we ensure that you have players in every state. But I think if you look at our numerical examples that we talk about here, I think this I2 or sorry, the event E3 is the regeneration part where we ensure that some mass of players are there. So
Okay, so
you can
something is done explicitly to sort of account for
yeah. So essentially, this can be thought of as players joining and leaving the system. So
and
you
but
have
the action part of it, I guess, is also non-trivial, right? Even if you had somebody in every state, they might like that. You need to have one player for every action, and all of those actions randomly selected
yes,
too.
you're right. Yeah, that is true. But again, these two assumptions are mainly for to actually like to show the convergence results. I think we have a theorem 4, which I didn't talk about here, but in practice, we don't explicitly ensure that the every action is taken or every state is taken, and which is why you can see in our numerical example, like with 100 agents, it doesn't really work well. But when you have more number of agents, it works better.
Okay, cool. Yeah, thank you. That was one of the questions. The other question was kind of in a similar vein, is when you go to finitely many players, the evolution of the mean field stops being deterministic, right? And then in fact, I guess we were only considering policies that act using the local state but not the mean field. So in the case with finitely many players, I guess each player is not facing an MVP anymore, or at least not a time homogeneous MVP, because the mean field is evolving randomly, right? Was that a problem at all for the real world learning?
No, I didn't understand this part.
Okay, sure. I can try to rephrase it. I realize it might have been confusing.
Okay.
The ZK sequence,
Okay.
when we have finitely many players, that thing is now evolving randomly rather than deterministically.
It evolves according to policy mu k, right? So
it does, but with finitely many players and like the sampling in that pseudocode, I guess like ZK plus 1 is gonna have like a probability distribution rather than
you're
being
right. Yeah. But again, when you compute, or rather, let's see, because when you compute like next MFE, you're saying this is like a sample, which is sampled according to this. Sorry for let me. Yeah, which is sampled. Yeah, which is sampled according to this phi, right? So you can have randomness in your policy as well as. Yeah, that's true. Yeah.
But I guess like anyway, maybe this is probably a question that would be better in writing than in out loud, because it's
Okay. I mean, you're right. I mean, as you have more number of players, you have a better estimate of your Z dash, which is your next mean field as well.
Yeah, I think my question was poorly worded. That's my fault. Sorry about that.
Okay. No worries.
Matthew, if you have any questions, I'll pause for a second and let you take over.
Okay, sure. I have one small question about the uniqueness. So you have shown existence of Nash equilibrium with strategic complementarities. In general,
Yeah,
I would expect that maybe there is no uniqueness of the Nash equilibrium, or have you thought about it? Or
I don't think we show uniqueness. That's right. It need
okay.
not be. Yeah. I don't think we've shown uniqueness. Yeah.
Okay, so there might be multiple solutions in that case.
Yeah.
I see. But somehow you don't use, I mean, whether it is unique or not, the convergence theorem does not rely on that somehow. It's like if there is one, it will find one. And
Yeah.
Okay.
Yeah, because even the policy, even your mu star need not be unique, right? So for a given mean field Z star, your mu star need not be unique.
Yeah, indeed. Okay, thanks.